going to do some problems from 5.3 and 5.4. I asked you to do 27 to 34, all of them. I'm just going to do the evens here because this is really easy to do once you get the hang of it, and you have the answers for the odds in the back of the book. So there you go. So let's go with number 28. So I've got a derivative function, sorry. So the first thing is when I go in here, I'm not going to take the derivative of this by hand. I want you to understand that what we're about to do is not some kind of shortcutting or cheating or whatever, or sticking it to the man. What we're doing here is it's a skill that we are expected to have. This first problem, I could take the derivative of that. It's not hard to do. You know, f prime is equal to 1/3 times this to the negative 2/3 times 2x, right? Big deal. Okay, I could find that and do that. But since I'm already committing to doing this problem using technology, I don't want to do it that way. I want to do it using technology, right, to fully exploit that. So how do you graph the derivative? What I would like to do is have a graph of the derivative to look at and then get all the information that I need from that graph. Now, I should have got a TI-84 with math print, so you could, because you guys probably have that. So what I'm going to do is I'm going to go to math number 8. That's my derivative thing. Now yours is going to look much cooler than mine. Yours is going to look like a little, yours is going to look like D, and there's going to be a little box there, and then there's going to be parentheses, and there's going to be a big box here, and then there's going to be like a line here, x equals, and then a little dotted box there. Something like that. Yours is going to look like. Okay, so D, what do I put in this box? An X. And then what do I put here? Here you put your function. For my way of doing this, and just in case any of you have an old calculator, I need to put the function first. So that's this. So that's x squared, in this one minus 4 to the 1/3 power. And that looks good. Right, and then a comma for me here. You don't need any commas for this. So this is where you're going to put your function. Your this. I'm not going to rewrite it there. And then the way that this thing works in the calculator, this finds derivatives for you, but it does it numerically by like number crunching, finding 2 points that are really close, like kind of like what we did at the beginning of chapter 3, thinking about how do you approximate, how do you get some kind of value for the tangent line when you only have 1 point? Well, you take two that are really close together. Of course, we know how to do limits, but the stupid calculator is just a little machine that can crunch numbers. So it actually takes 2 points that are super close and finds the slope. Now, what we want it to do, we don't want it to find the slope at some particular value. We want it to find the slope at all values as it graphs across the screen. So here, I put an X. Okay? To do this with an old TI-83, my syntax for that is going to be comma X. That's the first one of these. That's like that one that you guys put in. And then the second one, comma X, is this one. All right, so yours is going to look cooler like that. And then well, I guess I can go ahead and hit graph, just graph it in the standard, in the standard window, zoom 6. So we can start from there. But certainly we should be willing, ready to make adjustments as needed. All right, so first of all, are there any, like these little like spiky things in here? That makes me suspicious. Are there any values that I cannot plug into this? No, I'm taking cube roots. You can take cube root of anything, positive or negative, and there's no denominator, so there's no continuity issues. So these are like legit maximums and minimums. They're just pointy ones. Okay, so I think I would like to, you don't have to do this. I'm going to do a zoom box, and I'm going to make that box go around the stuff that looks like it's interesting and important to me. So I think I'm going to do something like this. Again, I don't think this is absolutely necessary to do this, but I'd like to get a little bit better look at that. Now remember what we are looking at now. This is a graph of the derivative. Oh, it looks like I missed the spike there. This is a graph of the derivative. Right? And remember that there are no undefined points on this function. So what do we have? We have there are going to be undefined points on the derivative of this, right? And we can see that, those undefined points. But the original function itself is defined there, right? That's that thing that happens when you have 1/3 power. You get the 1/3, everything's fine, but then you take the derivative and you get a negative 2/3 power, and that puts stuff in the denominator. All right, so can I answer all the questions that I need to answer just looking at this graph? Where are the critical points? So is that what we're being asked? Yes, critical points and inflection points. Critical points at x equals -2 and 2 and 0. Those are the places where the derivative is undefined or equal to 0. Right? And if you want to make sure, if you're like, I'm not really sure that that crosses at 0, you can go and find your 0. You can play the game with the cursor, or you can say, well, I know it's in between like -1 and 1. And that's 6.687 times 10 to the -10th. You know what that is? That's 0. That's 0.000, a whole bunch of stuff. Why is the calculator not telling us it's exactly 0? Because the calculator is a stupid machine. It's just crunching numbers, and that's what it came up with. But that is, we need to be able to interpret that as 0. All right, inflection points are the places where the second derivative changes sign. In other words, where the first derivative goes from increasing to decreasing. So the here, this goes from decreasing to increasing at -2. If you're like, wait, but there's no, it's not even defined there. The second derivative does not have to be defined. It is a defined point on the original function. So that means it is an inflection point because the concavity does change there. The second derivative does not have to equal 0. It can be undefined. So there's an inflection point at -2 and 2. So in general, we're looking for like maximums and minimums of the derivative when we're looking for inflection points. All right. Great. So the only other thing that you could say, and we weren't asked to do this in the directions, you could say whether these are maximums and minimums. Here we have this goes from the derivative is negative and then it's still negative, so that is not, that's a neither because it doesn't change sign. Here the derivative goes from negative to positive, so this is a minimum. Oops. This is a minimum. And at 2, this is also a neither. And you know how to justify those now. Okay, so that's the game. I'll go a little faster now through these other ones. How about, and notice they're doing all these ones with like the 2/3 kind of powers, 4/3, 5/3, things like that. They're giving us ones that have this interesting feature, these interesting features. So how about 2x squared minus 3x to the 4 thirds. That's not what I meant to do, so I need to... There we go. 2x squared minus 3x to the 4/3. That looks good. And graph, I think I should probably go back to my standard window so I don't get some weird bias or fake out about what's going on. Why is it graphing so slow? Because it's got to do a lot of number crunching for every single little pixel that it's graphing across here is a pretty intensive slope calculation. So it slows it down. Yours might be a little faster. Alright, I think I'm going to do that zoom box again. Probably the last window that I had would have been just fine, but oh well. You know the zoom fit feature of your calculator? You like using that? Well, you shouldn't. It's terrible. Don't ever use it. Okay, so here my derivative is crossing from negative to positive, so it looks like that's at 1. We'll check, and then, alright, so let's see what we can report here. I've got critical points. That's where the derivative is 0 or undefined. Looks like 1, 2, 3, negative 1, 0, and 1. Want to be sure. Second, calculate, find the zeros. There's one here. I'm going to say that it's in between negative 1.5. You can play the cursor game if you want. It's just so slow. I can't stand it. Negative 1.5 and negative 0.5, negative 1.5. That's definitely in between those. And take a guess. Bet you it's negative 1. Oh yeah. So same thing. What are you going to write down here? Can you write that down? No, that's negative 1. It's your calculator's lame, no-brain version of negative 1. So that's at 0. That's at positive 1. You can check them if you want. And what are they? They mins, maxes, or neithers? It looks like here our derivative goes negative to positive, so that is a minimum. Here we go from positive to negative. That's a maximum. And here we go from negative to positive again. That's another minimum. You can write out the justifications for those if you were asked, I'm sure. And then the critical points are the places where the derivative goes from increasing to decreasing. So that's happening at it's in between negative 1 and 0, isn't it? Look for the cursor to show up right there. Thinking. So it looks like my inflection point, first one is at negative 0.192, 3 decimal places for the College Board. And you think it's symmetric? You think it's got the same thing there? You think it's going to be positive 0.192? I think that's reasonable to guess that, but I'm going to be careful. Just check to make sure. Thinking. Wheel spinning. Yep, you were right. Okay, number 32. If you're wondering, why are we not just graphing the original function to find these maximums and minimums? That'd be fine, but then you'd have to do something else to find the inflection points. And if you're looking at the graph of the derivative of a function, you can find all the critical points and all the inflection points from that graph. So graph of derivative, pretty information-rich thing. Okay, so next one. At 5x to the 2/3 plus x to the 5/3. comma x, comma x. Ooh, that's not good. I've got a curly bracket in there. All right, I think that's good. I'm going to go back to the standard window. Uh-oh. See that little dancing thing? That's like bad news. That means it's frozen. What did I do? Why did it not like that? 5x to the 2/3 plus x to the 5/3, comma x, comma x. Parentheses. I think are okay. Oh, there we go. I don't know why my calculator got jammed up there. Oh, so slow. And so there's a place. I'll get this set up anyway. Critical points. Are going to happen at the minimums. So this is interesting, huh? It looks like somewhere, assuming that crosses at 0, I'm going to see, you know what, I really would like to see a little bit more kind of in there. So maybe from like -3 to 3. Let's go ahead and just manually set that. I know, I gotta wait for this again now. Sorry. Wonder how much, if at all, your TI-84s are faster than this. Alright, so this is pretty interesting. So remember, we're looking for places where the derivative is 0 or undefined. Those are our critical points. So that's going to be at x equals, it looks like it's probably at 2-ish, but I don't know that for sure. So I'm going to go ahead and find that 0 that's in between -3 and -1. Looking for the cursor to show up there. Thinking. Yeah, it's a -2. So then looks like there's some kind of minimum. I don't know if that's a spike there or something, but it definitely looks like something's going on here where it's hard to say what is going on there. So I think let's see. You know what we could do? We could go ahead and look at what does the original function look like. What does 5x to the 2/3? Your fancier calculator might do a little bit better job handling those things like asymptote kind of situations. And to avoid confusion, you know how to do this? I'm going to just hover over the equal sign and turn that one off. So I don't have to delete it. I'm just turning it off for right now so I can look at a graph of the original here. So probably this has some kind of cusp. Boink. Right there. So that's a minimum. So what's happening is my derivative, you can see there, that is a minimum, a critical point at 0. So the slopes are getting like super negative as it gets close to that point, and then positive after. So I think we have an undefined spot that's like an asymptote in the derivative graph, is what's going on there. And then I don't think it crosses again. And I think that's consistent with what we saw in the graph. That was the, those are the only things there. So this was a minimum here, where that derivative is undefined. And you could justify that because the derivative goes from negative to positive. And at -2, the derivative goes from positive to negative. So that's a max. Inflection points are the maximums and minimums of this. And it looks like we have one here. It's pretty shallow, but there's a minimum in there. And it's somewhere between 0 and 3. So I'm going to go ahead and find that. Locate that minimum in between 0 and 3. Guess. Yes, please. And that happens at 1. And now you're like, oh no, it's like 1.00. No, it's not. It's 1. That's just our calculator doing its best to approximate. Okay, so that's some calculator. Oh, sorry. I just wrote those answers. This is 32. I guess I'll write 34 here since I have it set up. So I guess I got one more of those. And let's see what we got here. Last one. I have, should have left my end deriv there. I've got 8 times the square root of x minus 1 over x. I think I handled my parentheses well there. You should use, if you've got the fancy math print going on your calculator, you should use the thing that will let you make an actual fraction so you can see where everything is. It's highly advisable. I'm going to go to Zoom 6, start with the standard window. Calculator doesn't like it for some reason. It froze up on me again. So let's try that again. Nope, it doesn't like, I bet it's parentheses. Open to parentheses, so I've got open, 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 close, close, yeah, I need another. That should do it. Now this has a square root in it, so notice that we have no domain over there. And then what's happening here? Is there like any kind of minimum here? Let's see if we can zoom in a little bit around there. So I'm just going to set this manually. I think I'll go from 0 to, I don't know, 10, sure, why not? And then here, we only have positive x values. So let's go from maybe 0 to 1, like zoom in right around the axis. Oh, it crosses, sorry. Of course it crosses. So let's go back to the window, and how about -1 to 1? Let's see how that looks. This is the graph of our derivative. Definitely crosses there. Keeps coming down. Oh, and then it goes back up. So it does have a minimum. So sometimes those things are a little tricky to see. You could zoom in more on that, but I think we're okay here. So critical points where this is equal to 0 are undefined. So I've got a 0 there. So second, calculate the 0 of that. Looks like it's in between 1, 2, 3. Definitely between 3 and 5. I think that's safe. Left bound 3. Right bound 5. Guess, yes please. That's at 4. And that would be a maximum because the derivative is going from positive to negative. And then inflection point, that would be the minimum that happens out here. Minimum of the derivative is going to be where the second derivative changes from negative to positive. So let's try to find that minimum. It happens somewhere out here. It looks like in the 7 to 8 range. So let's say it's between 6 and 10 or 5 and 10. That's pretty safe. And that's going to be my inflection point at 7.111. All right, that's how you do that kind of thing with your calculator. Great fun. And let's see, I did promise that I was going to do these in the same video, so let's see. You know what? I think I'm not. So look for a different video. Sorry about the false advertising there, but I'll put it in the, it'll be correct in the title. So I'll stop this one here.